Hey, Dr. Clark here, and in this preview video, we're going to look at section 2.1, solution curves and direction fields. Let's get started. So now that we're in chapter 2, you might be wondering, is this when we're actually going to solve differential equations? And the answer is yes. So chapter 2 is where we actually do some solving. But there's really three ways of thinking about solving differential equations. So the first way is what we call the analytical method, which is going to feel a lot like calculus. So using calculus to actually find the function. But there's also what we call a qualitative method, which is sort of thinking about the differential equation on its own terms and getting qualitative information about the solution. Should the solution be increasing or decreasing? Should it be leveling off? Should it go to infinity? Should it go to infinity in finite time? That kind of thing. And then there's, of course, numerical, where we feed the differential equation into a computer and let the computer tell us what the answer is. Eventually, we're going to focus a lot on this analytical method, but today we're going to spend some time on what's called the qualitative method. And the main qualitative approach we're going to take is to look at something called a slope field. Okay, so slope fields are a really nice way of getting qualitative information about differential equations. And the key idea is this. We look at the derivative, and in a differential equation, something like dy dt, where that's telling us about the derivative, well, the derivative is the slope of the tangent line. So really, differential equations are speaking the language of slope. Well, if a differential equation is dy dt equals some right-hand side, some function of t's and y's, then we could think about at every point ty, what is the slope? What would the tangent line look like? And essentially, we just make a plot that captures the essence of those tangent lines. And that plot is called a slope field. Let's start with a simple differential equation like dy dt equals y, where the slope is equal to the y coordinate. And to do that, we're going to need to use some software. There's one on the web right here that I've got the link for, but there's also a nice one that comes with some software program from a book. It does require Java loaded on your computer. I've got the links on Canvas for both of these. So let's take a break here, and then we'll jump into some of these software solutions. Okay, so this is the Desmos slope field generator. What you do is you put the right-hand side function here. In this case, we had dy dt equals y. And what that means is the slope of every line should equal the y-coordinate. So here, when the y-coordinate is 0, you can see the slope is 0. As the y-coordinate increases, you can see the slope increasing. Okay? Now, the t-coordinates are over here, but you'll notice the slope field doesn't change as you move in the t direction because the slope is defined just to equal y. So the slope is the y-coordinate, so changing the t-coordinate doesn't really affect the y. If you go for negative y values, now the slopes are negative, and the farther down you go, the steeper those slopes get. But again, they don't seem to change in the t direction, only in the y direction. So this is how a slope field works. Essentially, at each point, so here's the point 5, 5. The y-coordinate is 5, so the slope should equal 5, so you just draw a line with slope 5 at that point. Here is the point 5, 2. The y-coordinate is 2, so the slope should be 2 at that point. Here is the point 0, 0. The slope is equal to the y-coordinate, so the slope is 0, so you draw a little slope of 0 at that point. So Desmos has a nice little slope field generator for you, and you can plug in any equation you want. They've got it using x's instead of t's, but you could have something like x squared plus y to the third power or something like that, and it will give you whatever that is, a slope field for it, right? Okay, so that's how the Desmos slope field generator works. Okay, so the other slope field generator that I mentioned is that Java program that is linked to Canvas. It requires Java to run, but it is a nice program. It's called HPG Solver. And if you click that and you click Show Field, now I need to type dy dt equals y here, you can see it's the same slope field generator. It has the same property in that, the higher the y-coordinate you go, the steeper the slope is, the lower you go. And then if it's negative, the slope is negative. So it's the same dy dt equals y. What I like about this one is if I click at a single point, it actually draws in the solution to the differential equation. And you can see that solutions basically just follow the slopes. So if the slopes are negative, that solution follows the slopes down. If the slopes are positive, the solution will follow the slopes up. So now you can see the connection of a slope field with a solution to a differential equation. The solutions should follow the slopes. And so slope information is actually information about solutions to differential equations. Okay, let's jump into just a second example so you can see how this works on a differential equation that has both y's and t's in it. So dy dt equals y plus t. And we'll look at it on Desmos and on the other software program as well. Okay, so for the differential equation dy dt equals y plus t on Desmos, t has to equal x, so x is sort of the independent variable in Desmos, so we've translated that to y plus x, but y is your, your y prime here. And you can see for this one, well, let's go to the point 5,5. Well, now the slope should be, well, if the t is 5 and the y is 5, the slope should be 10 at that point. And as I go down to, say, the point 5,0, well, now t is 5 and y is 0, so 5 plus 0 is 5. So here you still have a slope of 5. Now, if I go to, say, this point right here, negative 5, 5, well, then the t is negative 5 and the y is 5, so 5 plus negative 5 is actually 0. So you can see you've got a 0 slope at the point 5, negative 5. And then as the y increases, the slopes increase. As the y decreases, the slopes decrease. But also as the t increases, the slopes increase. Because the slope is the y-coordinate plus the t-coordinate. So increasing t increases the slope, and increasing y increases the slope. And similarly, decreasing t will decrease the slope, and decreasing y will decrease the slope. So you can kind of see how a solution maybe that starts here would kind of ride up the slope there and then ride up the slope there. And you can kind of imagine how solutions might behave. Okay, let's jump over and see it in the other program. Okay, in the other program, we've got dy dt equals y plus t, and you can see the slope field looks just like it did before. You can find that spot right over here where the slope was equal to 0. But if we click, now you can actually see where the solution is that's riding those curves, and you can click anywhere and find what solutions look like. But at each point, for example, right here, I'm sort of at the point right around negative 1, 1, or negative 1, negative 1, so that should be a slope roughly of negative 2, and you can kind of see a slope of negative 2 drawn there. Okay, and then increasing the t's increases the slope, increasing the y's increases the slope. All right, so that's how this program works for the dy dt equals y plus t. Okay, so summing up, we've seen what a slope field is. We've seen a couple examples, but the main idea is you have right-hand side of a differential equation. That's telling you what the slopes of y should be, and so you just pick each point in the ty plane, use the right-hand side to compute the slope, and then just draw a little line indicating what the slope should be. Is the slope 0, 1, 2, or 3, or whatever it is, or negative 1, negative 2, negative 3. And if you cover the plane with those slopes, then solutions should more or less follow the slopes through the plane, and you can essentially solve any differential equation you want, using this slope field. Your solutions aren't going to be exact, but it actually will give you a lot of information about what the general behavior is. And, are solutions going up, going down, leveling off? Well, you can figure that out without having to do any solving at all. And so we are sort of solving differential equations, albeit in a slightly less than exact way. Okay, so that should get us started. We'll do a few more examples in class, and I'll see you there.